Thanks. So actually, what I'm going to talk about today is we'll probably have time to only talk about the first of these things, but this is all recent work that has uncovered some kind of, well, in a sense, surprising arithmetic structures that come up in certain, in models of gravity based on the spectral action functional, which I'll say something about in a moment. Actually, people here in the cosmology group have heard me talk about several other aspects of these models of gravity other times before. But this is kind of a first indication that there is some structure that are of interest to a more arithmetic point of view in it. So where do these models come from? So the origin of this type of thinking is actually coming from non-commutative geometry, although what I'm going to talk about today has nothing non-commutative in it. But the idea in the non-commutative geometry setting is that you can encode the information about a Riemannian manifold, so basically about Euclidean gravity, into a kind of algebraic package where essentially the information about the metric tensor, you package it into the Vierbein of the Dirac operator. And so your package, in the case of an ordinary manifold, would be smooth functions on the manifold, the spinors on which the smooth functions act by multiplication, and the Dirac operator, which in turn acts on the spinor. And the compatibility between these two actions is what gives the properties of the sort of formal properties of these notions, which is that the commutator is a bounded operator given by Clifford multiplication by one form. And the point is that the advantage of seeing these in this more abstract setting is that you can apply this formalism to other objects which are not smooth manifolds, and in a certain sense treat them as if they were smooth manifolds, and so in particular do some kind of gravity model on them. And in particular, the reason why we will develop this formalism in the setting of non-commutative geometry is that if you take a space-time manifold and you add some non-commutative extra dimensions, and you apply the same formalism, what this action functional produces for you is going to be gravity coming from the four manifold coupled to a matter sector that's determined by these non-commutative directions. And this allows you to create generate various kind of particle physics models with various properties. But for the talk of today, I'm kind of forgetting this extra non-commutative dimension and the particle physics sector. I'm just going to focus on a ordinary four-dimensional, Riemannian manifold. So I'm really talking about a Euclidean version of gravity. And the way one defines this action functional, so if you think of it in this spectral triple sense, what you have available is the Dirac operator. So you define an action functional that's built on the Dirac operator. So what you do is essentially choosing a cutoff scale and chopping off the spectrum of the Dirac operator at that scale. And then so that gives you a regularized trace of the Dirac operator, which depends on this cutoff. And that, so you are actually summing with a certain, you can think of the cutoff as some kind of smooth approximation to a cutoff function. And so you're adding up the spectrum of the Dirac operator under this cutoff function. So this looks a little bit strange as your choice of action functional. On the other hand, it certainly manifestly depends only on the Dirac operator and on the Dirac spectrum. And the thing is, so there's some other functions of the Dirac operator that you naturally have available, like the zeta function of the Dirac operator, which will come in a moment when you look a little more closely at this action functional, the spectral action functional.
Sorry, can I ask a question?
So the point where this becomes more interesting in a physics perspective is that when you yes.
That was the question.
Sure.
Sorry, could you go back?
Yeah.
So that S,
right.
why is it so much bigger than 0, I guess? Actually, what does it mean for it to be much bigger than 0?
So we're
the first line. The real part of S, you say, is much bigger than 0.
Yeah. So you want this operator to be trace class, right? So in general, what happens is that that's basically the sum over the spectrum, the absolute value of the react to some power minus s.
Right.
So if now you're on an ordinary manifold, right? So you have the while law that tells you how the spectrum of the Dirac operator grows, and it depends on the dimension. So in the usual case, this operator will be trace class when the real part of S is greater than the dimension of the manifold.
Okay, I see.
So in general, there will be some. So if it's sufficiently large, then that series will converge. And if you're taking an exponent that's too small, it diverges. So just the fact that the spectrum of the Dirac operator grows at a rate that depends on the dimension of the manifold.
On that point,
Yes.
are you assuming it to be about a closed manifold or compact or finite volume or something? So that are you assuming the manifold to have a finite volume in some way?
Yes, so yeah. So that's right. So for this purpose, you assume that the manifold is Riemannian and compact, because that otherwise you're right. The spectrum of the Dirac operator doesn't even have to be discrete, so you wouldn't. So you do think of working with a manifold that's compact and Riemannian.
So it could be compact with boundary or closed or just closed?
No, compact without boundary. If you want to introduce a case of a manifold with boundary, then you actually have to have some boundary terms, which is kind of like this extrinsic curvature part in the action function. So there's a version that you can do for manifolds with boundary, but for this purpose, I'm just taking compact manifold without boundaries. Okay, so the thing is, when you let this cutoff scale become large, you can look at how this functional behaves as in the limit of large lambda, in the large energy limit. And there is an asymptotic expansion, and the terms of the asymptotic expansion, so you have one term for each pole of the zeta function. So that's where the relation between this action functional and the zeta function comes in. So you have one term in this asymptotic expansion for each pole of the zeta function, and the coefficient of that term is contains the residue, the zeta function at that pole, and some momentum of this cutoff function. So there's some numerical parameters. You can think of them numerical parameters that depend on how you choose this cutoff of them. Okay, so the point is that these residues here, in the case of a smooth manifold, can be described in terms of some local expressions, so some integrals of some curvature tensors and so on. So and that's why you can think of these as a good choice of an action function for gravity, because although when you write it as trace of this regularized trace or cutoff trace of the Dirac operator, it doesn't look like it, but in this asymptotic expansion, it gives you back things that do look like what you expect to find. In particular, the reason why you can write these residues of the zeta function in terms of some kind of a local expression is because there is a relation between the zeta function and the heat kernel. And so the heat kernel itself has an expansion, an asymptotic expansion, where the coefficients are given by certain local expressions in curvature tensors and so on. And so those coefficients of the heat kernel expansion occur in these residues of the zeta function that go into the coefficients of the spectral action. Yes?
So I assume that most of these terms will be some non-normalizable polynomials in the curvature.
So you do have higher. So what you get is you have the usual Einstein-Hilbert action, and you have higher derivative terms. So in terms of renormalizability, the higher derivative term improves the situation.
So the question was, is it known how RG flow then would act? So RG flow renormalization will then change all of these infinite set of coefficients in
Right.
some way.
Yeah,
Is
so
it known
that's
how to
right. So you
deduct
mean
this
what?
kind of function?
Yeah, what is the renormalization for this? For
Yeah,
this
is it
action?
computable, the variation of the cutoff function with respect to the scale?
Right. So most of the renormalization group analysis that's been done in this setting really uses the because in general especially when you look at the case that also has a particle physics sector, the dominant part is coming from the renormalization group of the matter sector, and the gravitational part is
No, just for clarity.
so then, and so specifically about what the contribution of these terms, there is some work that was done by Walter van Soilekom on the normalized properties of the normalizability property and of directly of the spectral action functional, but there's not. I don't think the explicit correction term in the normalization group have been computed for these higher terms. I'll come in a moment to.
It would be interesting to know if the counter terms are still in this form.
Right.
If it brings you within this space.
No, that's a very natural question. Yeah, I agree. I mean, that's yeah. Anyway, for this one, I'm just going to look at these action functional, without taking into consideration counter terms and normalization. So I just look at this expansion as it is in this form with these coefficients that come from the spectral action actually. And I mean, indeed, it's an interesting question if one starts to put counter terms in that, whether actually the properties that I'm going to talk about in the moment will still be preserved or not. And that's so in general, the way one computes these coefficients, so if you are just in the case or in the manifold case, is via pseudo-differential calculus, because so you're looking at the heat kernel of the square of the Dirac operator. That's a second order operator. It has a pseudo-differential symbol that has 3 homogeneous components, and the fact that you write, so you can. Some of these usual formal spectral theory manipulations, like your heat kernel in this Cauchy integral formula. And so you want to compute these coefficients in the heat kernel expansion. Now, if the manifold is of dimension n, you have a term that depends on the dimension, and then you have the corresponding terms with these. So you're after these local expressions that describe these coefficients. And so a way to do that is to construct a parametrics for the Dirac, for the square of the Dirac operator, and that gives you a recursive formula at the level of the pseudo-differential symbols, a recursive formula for computing the coefficients of these parametrics, in turn by this fact that this is almost an inverse to that operator, so it gives you a relation between these coefficients and the terms of the symbol of the Dirac operator. And so you can recursively solve this and come up with expressions for the terms of the parametrics that depend on derivatives of the starting piece of the recursion that depends on the leading symbol, and then derivatives of the homogeneous pieces of the symbol of the square of the Dirac operator. And so in principle, that gives you a computation of these coefficients in terms of integrals of these terms in the parametrics. Problem is that if you sort of try directly to compute them with these methods, these computations become rather hard after a few terms. So you usually can compute like the A2, A4, maybe A6, but this quickly becomes a very large computation. So there's a method that works better and that simplifies this computation, which is to actually compute the terms you want as residues in a suitable sense. So there's a notion of residues for pseudo-differential operators that is basically ends up being an integral over the cosphere bundle of the manifold that involves the symbol. And the point about this is that let me show why this actually works better as a computational method than the parametrics one that I showed before. So the terms that you want to compute in the heap kernel expansion. So let me just go directly to the thing. So the term that you want to compute, so in the asymptotic expansion, become a residue in this operator sense of this formal inverse of parametrics, again, of this operator. And now, OK, let's come down more explicitly to what this means. So when you look at the first coefficient that you encounter that is non-trivial to compute, which is the A2, it becomes an integral on the cosphere bundle of this piece of so again, you can think of that in terms of these parametrics that I described before, but now you only need the first piece of this recursion function. And now the way you can get the other coefficients, instead of going into this recursive construction of the terms of the parametrics that become difficult, you just move the coefficients in the expansion by putting in an auxiliary space, which is a flat torus, which does not contribute anything because there's a Kunnert formula that splits out the terms of this heap kernel expansion. And these are coming from curvature tensors. So the only ones that are non-zero for a flat torus is the volume term. And so you're just shifting the index of which coefficient you're computing there. But you're always computing only the first term of this parametrics construction. So except you are computing it on this larger space that has these flat directions that don't contribute any curvature, any additional curvature. So this is just a simple geometric trick. Yes?
So I'm getting lost. So
yes.
in the first line, you have the trace of d to the minus 2. That's the reciprocal of d squared, I suppose.
That's right.
But but its trace would just be a number, I would think. But now you're integrating it over.
Yeah, no, that's the local. So no, the thing. Sorry, the thing inside the integral is the first piece in the symbol. The pseudo differential symbol expansion for this inverse of the square. So these parametrics for the square. And so that is an expression in the variables, in the pair of variables, which are variables on the manifold and variables in the cotangent bundle. Right, so you take the differential symbol is like your Fourier transform of your differential operator. So it has is a polynomial in variables. Whenever you're taking derivatives, it has a polynomial term. And so the variables are in this cotangent bundle, but then everything depends on the point where you are on the manifold. So this sigma minus 4 d minus 2 is a matrix in whose entries depend on coordinates on the manifold and coordinates on the cotangent bundle. So trace in there in the integral just means you take the trace of the matrix. So you get a function on the cotangent bundle, the sphere bundle of the cotangent bundle. And that's what you're integrating over. So the xi and x are the coordinates on the cotangent bundle and the manifold direction. And so that's what you're integrating over. And so that, so the point, the sort of interesting information apart from the formula itself, but the conceptual information that's interesting here is the fact that you only need the sigma minus 4, so you only need like the first piece of this expansion of the symbol of the parametrics for the square. You don't need, if you have to compute all of them, after a while you get this very complicated expression. Here you only need to compute the first one. And what you do is, so the problem is if you do the normal to the differential thing, when instead of A2 I want to compute A4 and then A6, so the odd ones are vanishing because of symmetry. But if I want to compute A4, A6, and so on, I would have to compute more and more of these terms of the symbol of the parametrics. Instead, what I do, I put in these additional flat directions. And then for each of them, I still have to compute only the first term of the parametrics. But the parametrics of this operator that is combined is a combined version of this d square and the flat Laplacian on the flat directions. The point is that those flat directions are only contributing a volume term, and there's no curvature. Okay? So all the other terms are only coming from the d square. So at the bottom, I'm still computing the coefficient of the d square that I want, but I'm computing them by computing only the first term of the parametrics for these combined operator. So it's kind of avoiding this long recursion thing for and makes the computation faster. Okay, and so but there's some other things that it does besides making the computation faster, which is what I'm going to come to. And so you get these all these terms. So that's going to be, so what we're going to look at, is these integrals, so a collection of integrals on the cosphere bundle of your manifold times these flat, so the manifold that has a product with these flat tori. And but in particular, I want to focus on a kind of manifold that has some very nice symmetries, and that's somewhat, particularly well behaved. And so I'm going to focus to the kind of manifolds that give interesting results for what I'm going to say here are, well, the Robertson-Walker metrics, where you have these S3, so you have this round sphere metric. And some generalizations, which are these Bianchi-9 spacetimes, which are no longer isotropic. So you have a different scaling factors in different directions, but you still have one SU2 symmetry, right? So it's not a round metric, but it still has one SU2 symmetry. So these are spacetimes that are sufficiently nicely symmetric that will produce better behavior of this action function. So I think I'll have time to only talk about the Robertson-Walker case. The Bianchi-9 case is, in a sense, more interesting, but it's a little more involved. So the Bianchi-9, so the Robertson-Walker case, so it has this round stream metric, and it has a scaling factor that depends on the time direction. So you just use the standard Hopf coordinates on the three-sphere. So you have these angles, and you write down the metric in this form in terms of coordinates. And you can compute, so we're after these Dirac operators and this heat kernel expansion of the Dirac operator. So you write explicitly the Dirac operator for this metric. So it's a matter of computing the frame in the spin connection in terms of an orthonormal frame, and the properties of the connection that comes from the Levi-Civita connection. So you can write explicitly the Dirac operator in terms of these. So it's known what this. So this is known for the Robertson-Walker metric, and in particular, you can write explicitly the pseudo-differential symbol for this Dirac operator on the Robertson-Walker metric. It's a bit of a messy expression. It involves these trigonometric functions in the angles of the Hopf coordinates, and it involves the scaling factor and its time derivative. So, but anyway, you have a completely explicit form of this pseudo-differential symbol. And so you can start this, construction of the parametrics for this symbol. And so there is this is the explicit, this is the symbol for D, and we want the heat kernel expansion for D square. So the symbol for D square is a function of the symbol for D in this simple way. So you have explicitly the P0, P1, and P2 terms for D square. Sorry. So they have the homogeneous components of the symbol. This is the differential. Yes.
I think I missed the first 10 minutes I was giving a talk as well.
Yeah.
What are we plugging the metric into a general action and seeing what we get?
Yeah. So what we are after is this. So the action functional is a trace of some cutoff function of the Dirac operator. So f is like some,
Yeah.
You choose a scale, say minus lambda, and you have a function that's like basically it's like a cutoff at lambda. So you're only counting the part of the spectrum of the Dirac operator that's within this cutoff. And then you look at what happens when lambda is large. And this is going to be a sum of certain coefficients, the alpha n. And so it has an asymptotic expansion, depends on these coefficients. And okay, these coefficients are a function of the coefficient of the heat kernel expansion of D squared.
And this. So it's not something that, because you were mentioning Einstein-Hilbert plus higher derivative corrections and so on.
Hmm?
So is it like you get Einstein plus higher derivatives,
right?
And then you just plug that metric in that expression? No, that's not.
Yeah, that's right. So in a sense, when you expand out this, when you expand out this heat kernel expansion, you get these terms that include the usual, Einstein-Hilbert and higher derivative. And so in particular, you want to compute all of this for that particular metric.
But I'm not understanding. This is a very complicated computation, but plugging a metric into the curvatures is trivial. I'm confused.
Well, if you want to compute the first couple of coefficients, that it's easier to do exactly like you're saying. If you want to compute the whole series, then what you want to get is a kind of recursive formula that allows you to compute the other ones in terms of the previous ones.
We want to use the symmetries of this metric to compute this in a faster way.
Yeah, I mean, the point is that when you go to the higher coefficients, so you know a priori that they are going to be some higher derivative terms in the curvature tensor, but to exactly know their expression, you can do that as in terms of some. Basically you can do that with this method. This pseudo-differential calculus method. And yeah, you need the first ones you need to compute explicitly the first ones, which is not hard with this particular metric, but then you need some good method to go on with the rest of the expansion.
What is the higher terms?
Hmm?
What is the physics of the higher terms? At low energies, I only care about the first one, right?
So that's right. So at high energy, the dominant terms, so the ones that have a positive power of lambda, or non-negative power of lambda, are going to be you are on a 4 manifold, so they're going to be the A0, A2, and A4. And A4 is like a volume term, so it's like a cosmological term. A2 is the usual scalar, so it's the Einstein-Hilbert. And A0 is the one that contains, it has the Gauss-Bonnet gravity, which is topological in dimension 4, and it has a Weyl curvature term, so a kind of conformal gravity term. So physically speaking, these are the leading terms when lambda is large. The remaining correction terms of the other A to N for larger ones are small compared to these ones at large energies. So in a sense, you can say, okay, purely for physical purposes, I can just pretend that this asymptotic expansion stops here. But what I'm going to say is that if you actually consider all of these terms, you see some more interesting structure that's going on for this type of very regular spacetimes that involves what happens with these coefficients.
Okay.
Okay, so let's see. Let me just quickly go through. If you look at the first term and you compute it with this residue method, you can write it out completely explicitly. I mean, it has, so, okay, let me just talk about the structure of this and what you have that are going to be useful properties of what I'm interested in looking at right now. Okay, so first of all, you only get terms, so you get a bunch of terms, and all the ones that only contain odd powers in the cotangent bundle variables are integrated out to 0, so you only have even powers there. All the numerical coefficients that occur in all of these terms are rational numbers, which is kind of a priori not an obvious property. Everything is as real or so there's no a priori reason why you should see rational relations between these terms, and that's kind of an indication that there is some type of arithmetic structure going on behind the scene. So what you can do is make a kind of change of variables on these integrals and rewrite them in a way that's more algebraic. And the reason why I want to do that is because I want to try to understand what is this kind of arithmetic structure that's showing up in these terms. So instead of these trigonometric functions that you have from the parametrization of the three-sphere in half coordinates, you make a very simple change of variables where you write these in terms of some other variables. So it's just a simple, very simple-minded manipulation of this integral by playing around with trigonometric functions. And what comes out of that is that this simple first coefficient, first one that you compute in this expansion, you can now write it as an integral of a certain differential form that is now completely algebraic in these variables. It has a polynomial in the numerator and in the denominator, and this polynomial is coming from a certain quadric and some hyperplanes. So it's defined, this is an algebraic differential form that's defined on the complement of where this denominator vanishes. Okay. And moreover, so the integrand is this simple algebraic differential form, and the locus where it's integrated is also a locus that's determined by algebraic equations. So it's again in these same variables, the locus of integration is just something that's described by polynomial relations, and so this kind of numbers, so the result of computing this integral is a number. And there's a particular class of numbers that are interesting in the sense that they're not necessarily algebraic numbers, but they are numbers that are computed by an algebraic procedure, which is integrating an algebraic differential forms on one of these semi-algebraic sets, which are defined by polynomial relations and inequalities defined by equalities and inequalities defined by polynomial relations. These numbers are called periods, and they are an especially interesting class of numbers from a number theoretic perspective. And so it so happens, because of all these curious facts and all the coefficients you have are rational numbers, this simple change of variable turns everything into an algebraic, and that the first coefficient of this expansion is a period. And is a period of the variety, the algebraic variety, where the differential form is defined, which is the complement of these quadric hypersurface and hyperplanes that appear in the description. So there's a similar computation for the A4 term, which may not go through very explicitly, but the structure is the same. You have an algebraic differential form, which again has a quadric. Now in a higher dimensional space, there's more variables, and there's some hyperplanes. So there's an algebraic differential form that again is integrated on a semi-algebraic set, which is again of a kind, so the volume form is also an algebraic differential form. The differential form is defined on the complement of a quadric, so the vanishing of this polynomial and two hyperplanes. And again, the domain of integration is one of these semi-algebraic sets that are defined by polynomial equalities and inequalities. Everything has rational coefficients, so it's algebraic. And again, this comes from a very simple-minded change of variables from trigonometric to algebraic functions. And so the same picture is sort of persisting actually to all orders in this expansion. Yes?
I'm lost again. So
yeah.
This integral is over some it looks like some 6-dimensional space.
So right. So yes. So the dimensions are working like this. So in this case, right here. What? Okay. So what is the number of variables that you have? So there's the dimension of the manifold, and that is, so you have the coordinates on the manifold and on the cotangent bundle. But you have also these auxiliary tori, flat tori, which are additional dimension, and you have to add one. Each one you go to another coefficient. You have two variables for these additional tori. And you have a bunch of other variables that you treat as, so in your metric, you have this scaling factor, this scaling coefficient, right? And its derivatives, which are also coming into these coefficients of this hit kernel expansion. So you can actually vary how this time dependence goes in this scaling factor. So rather than picking one particular time dependence, I just treat these as formal variables at the moment. So these are these alpha 1, alpha 2.
So you're expanding A as if expanding A in a Taylor series.
That's so the way you can think of this is that so you first kind of pick formal variables for this scaling factor and its derivatives. Yeah. And the moment that you choose one particular time dependence of the scaling factor, you are picking a curve in the space of these variables. So like you first look at how this just depends on this set of variables, considering them as independent variables. And then once you pick a particular time dependence, you are restricting everything to one particular curve inside this space of variables. Okay? So it's like you first describe this larger geometric setting, and whatever happens there, then you sort of specialize it on a particular locus that's defined by a choice of a curve with this.
One other question. The integral over the 3-manifold, that should be trivial because it's homogeneous. Everything is homogeneous. So shouldn't there be a way, instead of using these funny angular coordinates, just to make that integral trivial?
The integral on the 3-manifold part is coming in this variable here. So it's the dependence on these variables.
Uh-huh.
So in a sense, the reason why it's not new is because these variables go into defining where this form is singular. Right?
In the 3-manifold.
So.
Oh, no.
Yeah. So by the way, these integrals are convergent, so you don't have to worry about the singularities of the differential form creating divergences in the integral. The integral converges, so there's no like a regularization or normalization or anything. It's just that I want to write these integrals in a form that manifestly realizes them as periods of some algebraic variety. So I'm kind of concocting a suitable set of variables so that my integral becomes manifestly a period of something algebraic. And so this structure kind of persists for all the other terms in the expansion. And again, you are going to end up with a set of variables that corresponds to the manifold and cotangent bundle coordinates, and a set of auxiliary variables that corresponds to the scaling factor and its derivatives, which eventually you want to specialize on some curve, but you treat them as affine variables to begin with. And you use the similar set of coordinates. So you have a quadric hypersurface that depends on the coordinates in these geometric coordinates, and the ones of this set of other coordinates are the ones of these auxiliary flat tori that you are putting in at each stage to compute the coefficients by this residue method. So all the terms in this expansion have a very similar structure. They are all an integral of an algebraic differential form. The algebraic differential form is defined on the complement of a quadric and two hyperplanes. And they're all integrated on a semi-algebraic set that's defined by some polynomial equalities and inequalities. Everything is over rational numbers. So it's a period it's a period of this variety, the complement of this hypersurface in an affine space of a dimension that grows with so that the overall dimension grows with the term in the expansion that you're looking at. So what is the geometry? So why this geometry? Why am I interested in looking at this from this geometric perspective? So as I said, these period integrals, when I write them in this form, they're this kind of numbers that are integrals of algebraic differential forms on cycles defined by algebraic relations. And there's this general principle that if I know something about the variety, the geometry of the varieties constrains what kind of numbers are going to occur as these period integrals. And the type of object that describes the geometric property of the variety is a kind of universal cohomology theory for the varieties, and things are called motifs of algebraic varieties. And essentially, they come inside different flavors according to whether the manifold, the varieties you're looking at are compact or non-compact. In this case, it's a complement of some hypersurface, so it's a non-compact case, which is called the mixed motives case. And so basically what one does is one formally abstracts the property that a cohomology theory should have for these type of varieties, like long exact sequences, Mayer-Vittorius, some kind of dualities and homotopy invariants. Kind of formal algebraic properties that any good cohomology theory is expected to have. And this category of motifs of algebraic varieties has some especially nice subcategories, which are essentially generated by projective spaces. Those are like the simplest kind of smooth projective algebraic varieties that you can think of are projective spaces. And so the subcategory that's generated by those is like the simplest type, but I mean, it already contains a lot of interesting objects, but it's the simplest type of this category of motifs that you can look for, and those are called the mixed state motifs. So there's a parallel interesting story where these objects have made an appearance in physics, which is in quantum field theory, where you can try to write the Feynman integrals in an asymptotic expansion of, say, a scalar field theory as periods of some algebraic varieties in a similar way. You write the integral as an algebraic differential form integrated over some cycle defined by algebraic relations. And in the case of a quantum field theory, the place where these differential forms live it's also the complement of a hypersurface. The hypersurface has some quadric hypersurfaces, a bit like what happens here. But in the case of quantum field theory, there are some complications in the picture. One of them is the fact that these quadrics intersect in ways that are not easy to understand or easy to control in terms of what happens to the motive. And another reason is that there are divergences in these integrals. They are typically, there's a renormalization problem. So curiously, this spectral action expansion provides a kind of toy model for what one sees in this motives and periods picture in a quantum field theory setting, where everything that goes wrong in the quantum field theory setting works here without any problem. So the integrals are always convergence. You don't have to worry about any divergences. And the differential forms are defined on a complement of quadric and some hyperplanes, but these now intersect very nicely, so everything is under control in the way that these behave. And you can really control a lot more explicitly the motive. And unlike what happened with the quantum field theory, where surprisingly at some point people discovered that when you go far enough into the expansion, and far enough means 9 loops, so very, very deep into the expansion, you suddenly start to see motives that are not mixed state anymore. So this kind of demolished a lot of conjectures that people had about that thing. So here, that problem doesn't come up, and so you keep having motives that you can control very well. So it's a kind of a strangely parallel story, but very in the end much simpler to handle. So when you want to do explicit computations with these motives, with these objects, often what one does is one computes these kind of like Euler characteristics of motives, which are simpler to compute, which are the class in the Grothendieck-Rein of the motive. Is just isomorphism classes of varieties with a kind of inclusion, exclusion, and multiplication. So it has the same formal properties of an Euler characteristic. So it's kind of, in that sense, is thought of as an Euler characteristic of motives. And if one looks at the motives that come up in these spectral action calculations, so we have these complements of these quadrics and hyperplanes, and relative to some divisor that contains the boundary of the domain of integration. So basically, one has to describe what the motives of these objects are. And so the motives of quadrics are well understood. And there's some interesting things there. There are like some torsion phenomena that occur, but that disappear after you pass to a field extension. So there's a little bit of technicality about the motives of quadrics, but it's nothing really complicated. It's something that can be understood pretty well. So the piece that's coming from the quadric hypersurface is well understood. The two hyperplanes by themselves are also obviously things. So the hyperplane in a fine space is another affine space. And, so those are well understood. And the only thing you want to check is, because you're looking at the union of these hypersurface, you need to control the way that they intersect to make sure that the nature of motives stays the same. And so, okay, the quadrics that you're looking, the specific quadrics that you're looking at in each dimension are these ones, and you can inductively compute the motive of these quadrics from the one in the previous dimension. And so explicitly, you can compute this Euler characteristic for this motive to check that they remain in this mixed state world. There's some formal properties of classes in the Grothendieck-Rein that you can apply. And the bottom line of this series of manipulations is that this is the locus that you're interested in, the complement of these quadrics and hyperplanes. And you can write that out explicitly as a polynomial in the, so L is the class of the affine line. So anything that is a polynomial in L is one of these state motives that are these nicely behaved motives. So if you can write everything as a function of L, and so this all works because, so this, the class of a quadric hypersurface, as I said, is also going to be of the same kind. So the final expression is the one that one sees there. So it increases, the polynomial increases in complexity in n, but remains of this very simple form. It's a polynomial in the Tate motive for all terms. And so one can upgrade this the argument from the Grothendieck class, so this Euler characteristic-like object, to the motive itself, and show that the motive itself is in this Tate type, this Tate class. And this is done by applying these formal long exact sequences that you have for motives. Again, the point is that if you know, so you have a complement of a union of pieces for which you want to compute the motive. So you want an exact sequence that relates the complement, the motive of a complement to the motive of the thing. No, so the motive of the complement of a hypersurface with the motive of the hypersurface. You want another exact sequence that, if you're taking a union of things, relate the motives of the pieces, the motive of the union, and the motive of the intersection, and then compute each piece at a time, and then assemble together these exact sequences to get everything. So it's a series of steps in each one using one of these long exact sequences and combining them together. So it's like the reason why the class in the Grothendieck ring is easier to compute is because whenever you have one of these exact sequences, it simply becomes a sum of terms. So like the Euler characteristic. So it doesn't see the non-trivial extensions. When you want to upgrade it to the motive, you really have to keep track of these exact sequences with the corresponding maps. But the point with these arguments about motives is that you really, most of the time, are simply using the formal properties of these long exact sequences. In a sense, you don't have to explicitly compute the maps between them. You just have to know that certain things like taking unions and intersection give you a Meyer-Vittori sequence, that taking a complement gives you a Gisin sequence. So you just use these formal properties, and you combine them in the right order. And as long as there's enough terms that you can control, you're able to control the remaining ones. So this is the type of argument that you have. So okay, the bottom line is that in this setting, these motives always remain in state. So these periods are always periods of state motives. So it's like a kind of the optimal picture where everything that goes wrong with the quantum field theory story is working here. Now, of course, there's this interesting question that you were asking earlier, like what if I actually start to do something on this action, which is something that involves introducing counter terms, and will that still remain within the same type? So or would it change the nature of these periods in some way that makes it more complicated? Interesting, because this is really not. Well, in a sense, it's not considering quantum effects in a sense.
And this specific for Robertson block, right?
Right. So once you start to do that, what changes in this picture? So that's a kind of other story. So okay, let me maybe stop here. I just want to say that a similar story happens if you look at these more general non-isotropic versions like this Bianchi-9 metrics, where now you have more complicated hypersurfaces because you have these different scaling factors in all the three directions. And there's one thing I just gonna mention it quickly in words without going through it. Among these Bianchi-9 metrics, these anisotropic ones, there are some that are especially nice, which are these Bianchi-9 gravitational instantons. So these are the ones that are solutions of the Einstein equations and self-dual as metrics. So these are still Riemannian, not Lorentzian, but they are, okay, in quantum, they come up as these mini superspace models. So if you look at those particular Bianchi-9 metrics, the one that are, these gravitational instanton ones, they have a very nice. This is a fact that's known as an old result. They have a very nice parametrization. So they come in a two-parameter family. These solutions. They have a very nice parametrization in terms of theta functions. The reason why that's the case is because when you look at the Einstein equation and self-dual equations for these metrics, because you have this SU2 symmetry, instead of being PDEs, it reduces to an ODE, which is one of these singular differential equations of Painlevé-6 type. And the solution of those can be parameterized by theta functions, because they have to do with elliptic curves. And
do you know? You happen to know? I mean, there's a special case of Bianchi-9, which is there's a special case which is called tau nut.
That's right. Tau nut is a particular case.
Is that what you're talking about here?
It's a particular case of this class that I'm talking about right now. Exactly. So that should be one of these type of solutions. And
are they all hyperkiller?
Sorry?
When you say self-dual solution of Einstein equations, is the same as hyperkiller?
They are. Are they always hyperkiller? Maybe all of them are.
Is it always in dimension 4? Yeah, I think self-dual implies hyperkiller dimension 4. I think.
Right. Yeah. Anyway, the point about that is that if you use this fact that they have this nice parametrization in terms of theta function, and you plug that into this kind of asymptotic expansion of the spectral action, so you compute all these coefficients in terms of that parametrization of the metric. What you find is that all the coefficients, all these AN coefficients, are modular forms. And that is, again, saying something about what type of motives are coming up there. And it's still, so that's still something that I'm thinking about, so I cannot really give you like a punchline for that case. But it seems that that generalization of this simpler Robertson-Walker case has a lot deeper kind of arithmetic structure that involves things related to modular forms and so on. And yeah, so in a sense, at this point, just kind of leaving it as a kind of question of what is the underlying arithmetic structure that lives in this spectral action function under its expansion, and also what are the types of space-times that are likely to produce this kind of arithmetic mean. So obviously, these very symmetric ones, Robertson-Walker and Bianchi-9, but what else? Is there something else besides these things that one can obviously think of as the nicest, most symmetric kind of things? What other classes are likely to exhibit some kind of motives and periods or something interesting when one computes the spectral action?
Is it possible something like hyperkiller, which are algebraic complex manifolds?
Something, right? Yeah. Yeah,
I don't
like
remember what the Dirac operator looks like in the Bianchi structure. Like this is just a little bar.
Telvar star.
Yeah, there are various classes of gravitational instantons that are interesting, like this Chronheimer, Nakajima, so they are likely to have some interesting structure. And so there's probably several classes of this special type of Euclidean or Riemannian gravitational intensities that have that are likely to exhibit some structure of this kind, but.
Let's take Matilda and let's go with
Your question?
Just on your question, have you looked at the other Bianchi types? I mean,
so the Bianchi.
I mean, there's
the Bianchi 9 that are not gravitational instantons, or
I don't know. Maybe they're not. I don't know if any of them are what you call gravitational instantons. But there's other types. There's catenated, for example. That's a very simple one. It's rather. It's almost like a special case of Bianchi 9.
Yeah. So what? Yeah.
And it's simple. It would just be a torus, just a 3 torus, spatially speaking. And then there are others.
Right. So yeah. So probably
I think
what I expect, like from with if you just look at one of the Bianchi 9 that don't have any particular property, like they don't have they're not self-dual, they're not. Then what you see is something that's more similar to this picture that I showed for the Robertson-Walker, except that these hypersurfaces, they include these different scaling factors, so they become some more complicated objects.
All these special things you talked about are just for Bianchi 9. They're not for the Friedman-Robertson-Walker. Is that right?
So
I didn't understand. I mean, these nice features you mentioned.
Yeah, so you can just write the general kind of Bianchi 9, where you simply have 3 different scaling factors in the 3 SU2 directions, but you don't require necessarily that they are solutions of the Einstein equation or that they are self-dual. So if you just do that, it's really pretty much like this Robinson-Walker, except that you have 3 scaling factors instead of 1. So that kind of gives you additional variables in this, and the picture is kind of similar to the one that I described here. But it's more when you actually have more. So these scaling factors satisfy some equations like these self-duality equations, or the Einstein equation and the self-duality equation. Then those scaling factors are not just independent variables; they have a common parametrization in terms of some other variables, for example, these theta function parametrization and so on. So they're really not just they're not just independent variables in some way. They really live on some other geometric object, like an elliptic curve or something like that, and that makes the geometry more interesting. Okay, so that's why you see something that has this modular form property coming up, and you don't see it for a generic Bianchi 9 metric that doesn't have any of these constraints like self-duality and the Bianchi, the Einstein method.
Can I ask you a question on this?
Yeah.
Is it possible to interpret some of these things in ways other than using the spectral action? For instance, heat kernel asymptotics. Heat kernel is just a partition function of a mechanical particle within a magnetic. So could you say what you're doing just in those terms? I don't think you had trace of an operator in the posterior bundle. Of course, that's just the expectation value of an operator in quantum mechanics.
That's interesting. I don't think of that. Yeah. That's,
I mean, can everything be said, for instance, in terms of the heat kernel asymptotics without using the Bellin transform? Is the Bellin transform essential for the story?
So what do you?
Oh, I just mean, can you just use the heat kernel and instead of the spectral action? And then one is the Bellin transform of the other, as you explained. But do we need to use the Bellin transform, or?
You mean the modular form?
That's
Melon.
Melon.
Yes.
Do we need to do that, or can we just use the heat kernel?
Yeah, these results be stated just in terms of the heat kernel without reference to the spectral action?
Yeah, I mean the relation between the heat kernel and So, I mean, this is so there's two steps with that, right? When you expand in this large cutoff scale, first show that the coefficients are residues of the zeta function. And then you use this Mellin transform to relate the zeta function to the heat kernel and write the residues of the zeta function in terms of some gamma, some values of the gamma function and the terms of the expansion of the heat kernel.
Yes.
Right. So that's so the coefficients of the heat kernel expansion end up in the coefficients of the spectral action expansion through this.
Right.
Right.
So could you have given this talk without mentioning the spectral action?
So okay, you could just say, I mean, I just look at the expansion of the heat kernel.
That's
Yes.
right.
Yes. No, that's right. I mean, in a sense, the reason for interpreting these as these coefficients of the spectral action is because you think of this as the action functional for gravity, and these are the higher derivative corrections of your. So you know that these A0, A2, and A4 are just these volume form and Einstein-Hilbert action and this conformal gravity veil curvature, and then what comes next is these whatever higher derivative corrections you had when you interpret this as your gravity action function. So that's the main reason for thinking of this as the expansion of the spectral action as opposed to the expansion of the heat kernel. But yeah. So there's a purely interpretive viewpoint. I agree that for the purpose of the computation, you could just start directly with the heat kernel. And
these are the terms that would come out when if you were to integrate away a scalar field in that manifold. Is it correct to say that these terms are the ones that will be generated at one loop if you have a massive free scalar in that manifold and you're integrating it away?
I think so. I mean, you find the Green's function is related to the heat kernel. And if I have some background field, I will take some powers of the Green's function. That would look like the Laplacian minus n, which is what you were computing.
That's the ordinary Laplacian. Should it be involved with spin?
Oh, I suppose you could take a spin. You could take a spin.
Yeah, sorry, it's a massive fragment.
Yeah.
I wonder if that could be somehow useful to make some argument about the behavior of this computer.